Okay, it's recording now. So, okay, good, Lucas. The fresh perspective was helpful. So we're talking about last class where we talked about probability, and we covered very, very introductory random basic stuff. But the one thing I wanted to kind of say was, oftentimes when you see something as confusing, it's kind of good to fall back to ground rules. And one ground rule I think that helps, it's kind of a mnemonic, is whenever you see a random variable, just think of it as a vector, with the vector having all possible values that the random variable can take. And if you see a joint, if you see two random variables, a joint kind of distribution, just write them as a matrix. And I feel this view, always thinking of them as random variable is no big deal, instead of just one value that a variable carries, it carries a vector along with it. And once you think of it this way, many things, you kind of have the courage to handle anything that is thrown at you. And I personally, I think that helps. Okay. We talked about likelihood and posterior. We talked about marginalization. And we talked about, law of total probability. We talked about chain rule, and that's pretty much where we stopped. Worthwhile, I'm reading chat messages, worthwhile, so we can all use the same terms going forward. Yeah, true. Good. So today we are going to get into Bayesian filtering, okay, from scratch, from the very foundations. And let me see if I have any announcements before I get started. I hope you're reviewing the unlock paper. I hope your MP is going well. Once this MP gets done, the next MP is actually also kind of interesting, I feel, because you are going to start implementing hidden Markov models for motion tracking and stuff. So please keep going along with your homeworks and reviews, and please come to class. Again, I appreciate Jake. Thanks for turning on the video today. I appreciate Haufan, Anthony, as always. You guys are always have your videos on. So thanks, guys. And if anyone else wants to join in with their videos, you're very welcome. It's much appreciated. Great. So with that, let's get started with Bayesian filtering. Now, the motivation is the following. We said earlier that IMU-based motion tracking will diverge for sure. Right? You win the Nobel Prize if you can show that IMU-based filtering won't diverge. Okay. But we said that, look, we cannot do much over there, but we need, but maybe if we have additional information, then we could keep, wait 1 second, I have a problem. Give me 1 second, guys. Can you see this?
Yep.
Okay.
Yeah.
Good.
Start again.
You'll get to that. Okay, good. Yeah. So, so we said earlier that if we have additional information, maybe there is a way that we could keep the divergence in check. Okay. And what is the additional information? Well, there are many possible additional informations. One possibility is like unlock, where we used other sensor information to actually periodically reset the error. Okay. But there could be other additional information, and one popular additional information you can get is what are called motion models. And like we said last time, I think motion models are essentially some mathematical representation of the behavior of the object. There are certain things that you know about the behavior of the object, and if you can mathematically model it, then that is an additional piece of information that you should be able to use in conjunction with your IMU measurements, or any measurements for that matter, to better estimate or to keep the divergence in check. Okay, does that make sense? So we'll talk about all of these, but the point over here is that with additional information, we could keep the divergence in check. Okay, and in this particular, today's class, we are going to see how to actually use motion models to keep the divergence in check. Okay. So now, how would you combine / fuse IMU with motion models? That's the question. Okay. So by the way, what are motion models? We'll talk about it, but at a high level, if I tell you, or actually we're going to come to that, so maybe it's not a worry. Let's go to that one step at a time. So you are given IMU data here. You're given motion model. We'll soon see what motion model means. And you're asked, design an algorithm. You design an algorithm that combines IMU plus motion models and the output of that algorithm should be location xt, yt, which means the trajectory of the object that is moving. I hope that is clear, right? You're given IMU data, you're given a motion model, which is the behavior of the object. And now you're asked to design an algorithm which will combine these two in a systematic way and output xt, yt, where xt and yt are the coordinates of the object at time t. So this output is essentially a vector xt, yt, or x1, y1, x2, y2, so on till xn, yn. Very good. So what is a motion model? Okay, motion models are essentially behaviors or properties of the motion described in mathematical terms. Okay? So you're trying to say that, look, the object that is in question over here that I'm trying to track, they do not move in some random weird ways. Oftentimes, in most cases, there is some very nice structure to that motion. If there is a structure to that motion, we should be able to leverage that information if we can express that motion mathematically. Great. So let's look at some example motion models. One is a Brownian motion model, which is probably the most unpredictable motion model. And in that, we can say the Brownian motion model on a 5x5 grid, let's say this is a 5x5 grid, there are 25 boxes, and a particle could be in any of the 25 boxes completely randomly, uniform randomly. Right? So we would say the probability that a particle jumps from location Li to location Lj is 1 by 25, right? And particle goes to any of the 25 boxes with equal probability and its uniform distribution. Does that make sense? So this is one motion model where if you put an IMU on an atom, let's say, and now you try to track the atom's motion, you pretty much have nothing from the motion model, because the motion model is essentially saying, if the particle is at this location over here, there is no information that you have on where the particle could be in the next time unit at the next time step, because the particle can go to any of these other boxes with equal probability, right? That's like, yeah, I mean, we have a motion model, but we cannot utilize it in any meaningful way, because the motion model does not check where the particle could be next. The motion model doesn't tell me anything about where the particle could be next. So this is the motion model, but a bad one. It doesn't give me much information. Let's look at another motion model. And this time, let's look at what would be a car's motion model on the highway. Okay. So this is a car. This is the highway. And these are exits on the highway. Right? So a motion model and these are essentially locations 1, 2, 3, 4, 5, 6, 7, 8, so on till n. So now you can say certain things about the behavior of the car. For example, there's a high probability of going straight around the speed limit of that highway. Right? So you can say, look, if a car is at some location 3, there's a good probability that the car would go to location 4. Let's give that probability equals 0.7. That is a very good probability. Then you can also say there is a low probability of going far below or far above the speed limit. Right? Let's give that probability maybe 0.05. Very small probability of driving backwards. Maybe this is 0.001. Small probability of stopping on the highway. Maybe you have some emergency and you stop, right? So that's the probability where you stop on the highway. Maybe that's 0.01. Right? And you can now do more of these things, and together you can capture the behavior of the car, the behavior of the car's motion on the highway. So this is a more meaningful motion model. And the idea is, if you see that your car is at location 4 and it's moving at around speed limit, and then your IMU suddenly says this car is not moving, now you have a question where you have to say, do I trust the IMU or do I trust the motion model? If they are not in agreement, we need to somehow combine them, average them, maybe based on the trust that we have on the two of them. So if you've heard of things are called belief propagation, Bayesian inferencing, we are now in the territory of those kind of techniques. Okay, and all of that I think will become clear. But as long as you understand what a motion model is intuitively, at this point, you're in good shape. We are trying to capture the motion of an object through mathematical terms. And we have not yet done the math. We are just saying at a high level, a car's motion model could look like this. Questions thus far? Very good.
Could you
Yes.
just, sorry, could you just repeat what You said Bayesian filtering, and what else is the other term that they use for this?
Belief propagation.
Okay, thanks.
Okay. So now a popular way of expressing motion models is what is called a transition probability matrix. Okay. So transition probability matrix essentially says, this is my current location. This is my next location. Okay. And let's say I can be at a location 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. These are the 9 possible locations, let's say in a shopping mall or for the car. And the question we are asking is, if your current location is 1, what is the probability that your next location is 1? If your current location is 2, what is the probability that your next location is 2? And so forth. Okay. So let's say the probability that an object is static is 0.05. Right? If an object is static now, it will be static in the next time instant, or the next location will be the same location. Let's say that probability is 0.05. So then 1, 1 is 0.05. What is 2, 2 in this matrix?
Still the same.
It's still the same, right? So as you can say, the whole diagonal is 0.05. You agree, right? Very good. So we have modeled static behavior. Now we say, okay, look, if the current location is 1, then the next location being 2, that is that the car is going at a slow speed. Okay. Let's call that probability. How much should we give it? Let's say 0.2. Okay. So 1 to 2 is 0.2. What else is 0.2, do you think? If 1 to 2 is 0.2.
Every box that's like one step to the right of the diagonal.
Exactly, right? All of these are 0.2. Because we are saying that if you're in some current location I, the probability of going to location I plus 1 is 0.2. So that thing holds for every I. Right? Because you're saying that, oh, your velocity being slow is 0.2. Let's say from 1 to 3 is 0.3. From 1 to 4 is again 0.2. And maybe 1 to 3, that distance per unit time, that may be this, let's say the speed limit, right? So the speed limit is when you're going from 1 to 3, from 2 to 4, from 3 to 5, that's the speed limit. So when you're at the speed limit, that's the highest chance, which is 0.3. Below the speed limit is 0.2. Above the speed limit is 0.2. And very, very much above the speed limit, let's say is 0.1. And you're driving crazy, let's say that's 0.05, 0.05. Let's see if this adds up to 1. 5, 8, 9. Does it add up to 1? Five, 8, 9. Wait. This is 5. This is 0.8.
You're like 8 point something. I don't think that's 9 yet.
That's 9 yet, right? Let's make this that's 9. Okay. So if you're at location 1, you have characterized what is the probability of going to location 1, location 2, location 3, location 4, everywhere. Right? This is one character. This is a motion model. In fact, this motion model says that this probability is the highest, and maybe that's the speed limit. Going around the speed limit, there is some probability, but not as much. Stopping, the probability is very small. Going super high along the speed, above the speed limit, very low. Some people sometimes are in a rush, and therefore they go at much above the speed limit with some probability, right? This can very much be written out in English as a motion model, as a behavior of the car. If that's the case, you can write the rest of it. Can someone tell me what is this value? Oh, we haven't talked about that value yet. Let's say we say that going backwards, that probability that only happens in some James Bond movies, okay, where you're going the wrong other way, right? So maybe that probability is 0.001. Okay, let's for now let's put it 0, because otherwise we need to add up everything to 1, right? For now let's put it 0, but if that was some other value, we need to adjust all the other probabilities so they all add up to 1. Okay? So now tell me, 2 to 1 is 0, 2 to 2 is 0.05, because this is static. 2 to 3 is 0.2. What is 2 to 4?
0.3.
0.3. 2 to 5?
0.2.
Correct. You get the drift, right? Basically, this is coming here, 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 and so forth. Very good. What is 3 to 1?
Would it be 0?
0. What is 3 to 2?
0 as
Still
well.
0.
0 as well. 3 to 5? 3 to 5 is the same as
0.3.
0.3. Same as 2 to 4, right? I think you get the whole picture. Okay. So each element is the probability of transitioning from one location to another. So if I give you this motion model for this car, from location 1 to 9, and let's say this is the last location 9, right? You have pretty much a good understanding in terms of mathematically, in terms of probabilities of if a car is here, where is the car likely to be next? We intend to combine IMU measurements plus motion models to prevent divergence of object location or trajectory. This is the motion model. This is one way of expressing the motion model. There could be many other ways of doing it, but this is a popular way. And the way we combine IMU measurements and motion models, that one of those techniques is called hidden Markov models. And as we will talk at the end of this topic, that hidden Markov models can be used in many, many other applications, not just motion tracking. For example, I'll just give you a quick sneak peek. Handwriting recognition. Okay. You take a picture of someone's handwriting. I write something like that. You take a picture of that. That picture essentially, if you take this picture, it essentially becomes pixels. So my H would look like that. This part of the H is this part. So those are my measurements of where the pixels are that are black. Right? I mean, suppose I write it, or which pixels are red and which pixels are yellow. These pixels would be yellow and the writing pixels would be red. That's my measurement. My motion model is now no longer a motion model, but my motion model is, I know that A has to be this shape, B has to be this shape, H has to be this shape. Right? Someone cannot write an alphabet which is like, that is not an alphabet, right? Or this is not an alphabet, right? So I have some measurements, I have some models of what the alphabet should look like. And from that, I need to combine those two to decode what is the correct alphabet that the user has written, which is HELLO. We can combine those two, the language model, which is English language's letters, plus camera measurement, camera measured pixels, which is our IMU or motion measurements. And we can again decode what the person has written. So you see, hidden Markov models are a general technique of combining measurements with models. We are looking at it from the lens of motion tracking, but need not be. This can have many other applications. We will talk about them once we have covered hidden Markov models. Questions thus far? Questions? Okay, very good. So you're following so far, so good. Okay, let's now start with hidden Markov models, and let's look at it one step at a time systematically. Let's say a person is walking. Okay, and to make things easy, let's say that the person has, okay, let's say a person is walking and the person can only walk in discrete locations, meaning every time the person moves, the person will either be in location L1, L2, L3, all the way to location LK. It cannot be at location L3.5. We are just making it easier by saying that the locations on which the person can be are discrete. Are you all cool with that? Good. Now, let's say that time is moving in this direction. Okay, so this is time T1, T2, T3, T4, ... Tn. Time is moving in the vertical downward direction. And at every time, the person is making a measurement. Let's call those measurements M1, M2, M3, so forth till Mn. Okay. Very simple, right? At every time the person is making a measurement, and the person at that time instant can be anywhere among these k locations, and those k locations being L1, L2, L3, L4, L5, L6, L7, all the way till Lk. Similarly, at time 2, the person can be anywhere here. Time 3, the person can be anywhere here. All the way till time Tn, the person can be anywhere here. Clear so far, right? There's nothing non-trivial. Very, very simple. Very good. Okay. So now if you think of a person's walking, a person who's walking is essentially jumping between these points, right? So let me ask a quick question. Is this a feasible trajectory?
Yeah.
Okay, Eric says yeah. If that is the feasible trajectory, how is the person walking?
Forward or stationary at any point if possible.
Okay, Eric, think about it. What is the time? The time is T3. You agree?
Yeah.
The time is T3, but the person is at all these locations. That is like it's a quantum person.
Oh, okay.
Right?
I see.
That person does not exist yet. Okay.
Oh, so
So-
are those sorry, are those like dots? Does that mean like they're at, so that means that they're all at the same time, basically?
Yeah, at
Not
the same
just
time, right?
those.
Because time is
Okay.
T3, right? So you cannot
Okay.
do that, right? Very good. So if a person is walking in a straight line at a constant velocity, that trajectory should look like what? Someone?
Straight sideways line.
Huh?
Like a line with some slope, basically going through all the
Correct.
different rows.
Exactly. That should look like that. Right? Okay, very good. Hey, why won't this change? Very good. So here are some trajectories that I have drawn out. Let's label these trajectories. What would you call this trajectory? What is the person doing? By the way, the initial location of the person can be anywhere. It need not be L1. We don't know where the person is, right? The IMU is making measurements M1, M2, M3, M4. But you don't know where the initial location is. The person could be standing here too. That's fine. Okay. So tell me, what would you describe this trajectory as in English language?
Someone standing still.
Standing still. Very good. What would you describe this one as? Roughly.
Just going
Walking forward.
Huh?
Walking forward in a constant velocity.
Correct. Walking forward with roughly constant velocity. I said roughly because I didn't make sure that the slope is always straight. Okay, what is this one?
pacing around, I think.
Say that again.
Going back and forth.
Ah, pacing around. Very good, right? So this part is the static part, right? So it's like someone who's gotten out of the house, then forgot to lock the door, came back, paused at the door, locked it, and then again went back, right? Or maybe pacing back and forth. I think I like pacing back and forth. Pacing back and forth with short pauses. Right? because these are pauses. Right? Very good. So these are basically different kinds of trajectories. And now you see, right, I can pretty much, any walking trajectory that the person goes through, I will have a corresponding colorful line for that. Can you convince yourself of that? There is no trajectory possible that I cannot capture through this grid that I have drawn. Agree? And my probability transition probability matrix over here would also give me, would also captures all the informations. Hey, by the way, can this happen? Is that trajectory possible?
You can go.
You cannot analyze here. Good. So probability transition matrices also very nicely align with this kind of a model, because now you are basically modeling everything as a movement from one location to the next, and you could potentially express that motion through some probabilities. Very good. So now the hidden Markov model's goal is take measurements M1 through Mn as your input, and the transition probability matrix as a second input, and then output the estimated motion trajectory. Cool? That's the goal. Okay. So let's formulate this as a state transition diagram. So let Sk denote the state of the object at time k. Let Sk denote the state of the object at time k. So Sk is now a random variable. Guys, does that make sense? Sk is a random variable. Whenever I say random variables, you should have a vector pop up in your mind, where the vector takes all the values that the random variable can sample. So now tell me, what is this image that pops up in your head for this vector? What should that vector have? Someone?
Locations.
Locations what? Very good. Give me, what should that vector contain?
L1 through LK.
L1 through LK, perfect. Right? That's basically the vector. For all k equals 1 to n. Sorry. I shouldn't have written that. This is k equals n. No. I don't need to write anything here. Sorry. Okay. So Sk is called the state variable. If you've heard of state space methods, this is basically the gateway to state space methods. Okay. So Sk is called the state variable. So the human's walking motion can now be captured in the following: S1, then you go to S2, then you go to S3, and you keep going all the way till Sk. Sorry, Sn. Because you have time going from T1 to Tn. Time goes till Tn. And time goes till Tn. Okay. And, oh, I made this Lk. I should have made that LR, guys, because we made L go to R. Does that make sense? Yeah. So let's change this K to R. Remember, we have R locations and N time. So I can think of the human's motion as going from state S1, where S1 is a random variable, to state S2, where S2 is another random variable, to state S3, and S3 is another random variable, and so on. Right? And the measurement and motion model is available for each state. So now I can write from state S1 to S2, I have a probability matrix, a transition probability matrix, which is P1J, which is the row of that matrix, the first row, because you are at state 1, S1. Actually, I should be clear. I think I should make it Pij. I'll tell you why. First of all, let's ask what are all the values that S1 is carrying, or what S1 can take. All the values of locations, right? L1, L2, L3, all the way to LR. Right? So S1 can be everything till LR. And now we are asking if S1 is in some Li at time 1, that means, again, let me say this, if the user, if the human is at location Li at time t1, then S1 equals Li. Right? This means human at location Li at time equals t1. And now I have, from between these state transitions, I have this probability matrix, which is the transition probability matrix, that gives me information about what are the probabilities from S1 to S2. S2 is also a random variable. And at each point, I have a measurement, which is M1, M2, M3, and so forth till Mn. So look, S1 can take all these values. S2 can take all these values. S3 can take all these values. Sn can take all these values. And Pij tells me if S1 is L3 at time t1, then what is the probability of S2 being L4? What is the probability of S2 being L3? What is the probability of S2 being L2, and so forth? If you get this part of it clear in your head, everything will become clear. Any questions thus far? The transition probability matrix, let's say, said that going from location 2 to location 1 is 0. Going from location 3 to location 2, or even to location 1, is 0. So that means you can say, in this situation, going from S1 equals, let's say, L2 to L1, this probability is 0. because the transition probability told us that, right? Transition probability said that PII equals 0.05, which means being static is 0.05, right? That means if S1 is L2, then staying at L2, that probability is 0.05. If S2 is L2, S3 being L2, that probability is also 0.05. Right? So we have these transition probabilities from our motion model. And we also observed that any trajectory that the user can walk will be captured through these lines. Right? We have the whole space of possibilities captured in this model once we have the measurements, once we have the transition probability matrix, and we have these random variables that are connected by these probabilities. Hidden Markov models basically play with these models and they say, I'm going to develop a technique which is going to take these measurements at every state, and it's going to get the probability values of this transitioning between states, which comes from the matrix. And I'm going to combine these measurements and these probabilities to estimate what these S1, S2, S3, all the way to Sn, what those random value variables, what values will the variable take. So the key question here is, one second. Yeah. The key question here is, where is or was the human at time tk? So let's say this is tk, sk. At time tk, this sk equals some vector which contains L1, L2, L3, all the way till Lr. And the question we are asking is, at time tk, where is the human? Where is the human? That value is whatever is the value in sk. Whatever value the sk random variable has taken. Right? And the sk random variable could take many values. Obviously, it's a random variable. It could take different values, but with different probabilities. Remember, we said that in the beginning, right? A variable, a random variable is nothing that is, it's a variable that takes different values, but not maybe with equal probability or maybe with different probabilities. So if sk takes different values with different probabilities, we are essentially asking which value has the highest probability. So if sk turns out to be L3 with the highest probability, then our hidden Markov model will say at time tk, I am guessing the user was at location L3. This is the setup. Okay. So where was the human at time tk? And mathematically, you write that as, what is the probability of sk given M1 through K measurements? What does this mean? Probability of different values of sk given all the measurements until time tk. This 1 colon k basically means, actually, let me just move this a little bit here. This basically means probability of sk given M1, M2, M3, comma, all the way till Mk. Given all these measurements, what is the probability of sk? Right? I've seen all the measurements thus far. I know the motion model. Tell me what my sk value is right now. Now, this is basically what is called online tracking, meaning as the user is walking, you get the data and you're measuring where the user is. You can also do offline tracking, which is probability of SK given M1 through N. What does that mean? Google gets all the users' data. And 3 days later, Google runs algorithms on all the data from time 1 to time N. And from that data, it figures out where the user was at time tk, where k is less than n. So this is offline, meaning you have the full data. From that, you're figuring out what happened in the past. Guys, does that make sense? Please ask questions if anything is unclear. So this is offline. This is offline. This is online. This is real time. M equals 1 to k. This you cannot do in real time because data of M k to n, you don't have that data in real time. Very good. So hidden Markov models talk about both these kind of estimations. And this is an estimation problem because you're estimating what the maximum, what SK is, what the values of SK are from all these measurements. Good. Do you have an intuitive feel for probability of SK given M1 to N? Right? This is where we are going to start getting into mathematical symbols. So I hope you have a intuitive feeling. Whenever you look at these kind of things, it can look, whoa, what is going on, right? But again, it's not at all hard. Let me ask this first question. Is this posterior or likelihood?
Posterior, I guess,
Okay. Why is it posterior?
because M1 through K is evidence, is something that you measure.
Mm-hmm.
And
Okay.
so it's like hypothesis given evidence.
Very good. And what did we say last class? The hypothesis should have what property?
They should assemble the sample space.
Exactly, right? And in this case, SK is what? L1, L2, L3, all the way to LR, right? And and you know that the user has to be in one of these locations. So the random variable is essentially sampling the whole sample space. Make sense? Questions. This SK, the values that the SK can take are all the possibilities that are there, and you want to find one of those possibilities. Of everything that you're trying to find, if that variable captures all the possibilities, then you have it. Right? So this is indeed a posterior. Very good. Now, just to keep everyone in sync, I'm going to just quickly unpack everything here. If this makes you feel uncomfortable, it should not. And let's unpack it. Can you hear me, guys?
Yeah.
Can you hear me now? Yes. Okay, good. Okay. I hope the recording continues. Last time it did. I think again today we are having some issues with Zoom. Okay. So M1, M2, Mn, okay. Let's say these measurements are not IMU but GPS. Right? So your GPS is giving you some measurements of where you are. It could be wrong. Right? So what would GPS measurements be? GPS measurements will also be L1, L2, so on till LR. M2 would be L1, L2, all the way till LR, and so on. If this was IMU measurements, then these would not be L1, L2. Instead, for IMU, these would be some accelerometer values. And let's say the accelerometer value can be anywhere from 0 to 15. Right? So then it will be 0, 1, 2, all the way till 15. If this was accelerometer. Is that clear? Guys?
Could you repeat it again?
Yeah. So we are asking, let me delete this. We are asking what SK equals L1, L2, L3 all the way till LR. Done. What is M1? M1 are basically all possible measurements that you could have. Right? Guys, can you hear me? It's somehow okay.
Yeah.
Right? So M1 could be, if this was an accelerometer that measured acceleration from 0 to 15, right? If it was gravity, it would only give you 9. If it would give you 10, let's say. For some other values, if the object is falling in free fall, it would give you 0. So if this was accelerometer, then it would give you 0, 1, 2, all the way till 15. Okay. If it was GPS, right? And GPS is erroneous, remember. So you cannot say whatever is the GPS value, that's exactly my user's value. GPS is also erroneous. So you can do a hidden Markov model combining GPS and the motion model. That is also possible, right? In a New York or Chicago kind of a downtown, GPS is all wrong. GPS bounces around like crazy. So you can take the GPS value, you can take the user's motion model, and you can combine, and there also you will get better motion tracking. So I'm saying if this M1 was GPS, then it would have L1, L2, all the way till LR. Does that make sense, Jake? Right. So this M1, M2 till Mn depends on what sensor you're using to get your measurements. And I'm just going to write this as L1, L2, L3 over here, just thinking this is GPS. If it is accelerometer, then it would be 0, 1 to 15. Right? Whatever sensor you have, whatever values it can give you, you have to write down those values. Okay? Very good. So now SK M1 to N can be written through Bayes rule as SK comma M1 to N divided by P M1 to N. I hope you remember Bayes rule. P A given B equals P A comma B divided by PB. So if you write it that way, what is your numerator? Your numerator is the joint distribution between SK and all the measurements. Right? How many dimensional space is that? Remember, we were writing the joint distribution as something like that, right? And we were saying this is the joint distribution. Do you remember that we were drawing that surface? You're saying that's the distribution surface. So tell me, in this case, what dimensional space? How many axes are there in which we are trying to understand the joint distribution? Okay.
Is it n+1?
Perfect. Perfect. This is n+1. Right? N measurements and one SK random variable. SK could be any one value. Right? So you're saying this joint distribution means all these measurements, all these Mn measurements, and this SK value. What is the probability that I see SK equals L1 and all these measurements M1, M2, M3, Mn? What is the probability that I see SK equals L2 and all these measurements M1, M2, M3, Mn? And those probabilities are now shown in this blue surface, which gives you the joint distribution. Now it's no longer joint between two random variables, it's joint between n+1 random variables. Joint distribution of n+1 random variables. Very good. So this is your numerator. And this is your denominator, which is your Pm1, M1 to N. Right? Very good. Now look, from this joint distribution in the numerator, you want to know which value of Sk was the max probability given the M1 to N measurements you already have. Make sense? Because you already know the measurements, you already know what these values are. You know the denominator, the denominator values. You also don't know the numerator values, that M1 was this, M2 was this, M3 was this, Mk minus 1 was this, Mn minus 1 was this, Mn was this. You know those values. You also know the denominator values, because the measurements are given to you. Right? The Sk is not known. Very good. The denominator is same for all Sk, L1 to Lr, because those are given. So only numerator matters. Guys, do you agree? Only numerator matters? Only numerator matters, but the problem is we do not still know the joint distribution in the numerator. You know the values of M, but you do not know what Sk is, and you do not know the joint distribution. You do not know that surface, right? So then what you can do is you can turn this posterior to likelihood. And you write that numerator, which is this joint distribution. This is the joint, this is the numerator. This joint distribution, you can now write that as a likelihood, which is P M1 to N given Sk times PSK. Does that make sense? Why? Because remember again Bayes rule. PAB, A comma B, which is the joint distribution, is nothing but P A given B times PB, which is exactly what I'm doing over here. I had the joint distribution of these two over here. I made that M1 to N given SK times PSK. Guys, what do we call this? This is evidence given hypothesis.
Likelihood.
Likelihood. What do we call this?
Prior.
Prior. Perfect. Okay. So we've converted this into a likelihood and a prior. Denominator, we don't care. Okay. So this is likelihood. And that is not hard. Likelihood is not hard. Why? Because likelihood is saying your sensor tells you that you are over here. Sorry. Likelihood says, I am telling you that your location is this. What is the probability that your measurement is so much? Right? In other words, you are in a city, Chicago downtown. Your GPS tells you you are here. This is what GPS tells you. I tell you, look, I'm telling you for sure you are here. This is true. Now tell me, what is the probability of your measurement given the true location? Which is saying, what is the probability that you have this much of error in your GPS? That you can find from a data sheet of GPS, which says in Chicago downtown, there is a distribution of the GPS's error, that the GPS is slightly erroneous. There's a probability that GPS is more erroneous. There is another probability. You get this kind of a distribution of your sensor from data sheets, or GPS will tell you that, oh, the GPS will give you concentric circles saying the probability of being within 2 meters of the actual location is 0.7. Probability of being within 5 meters is 0.9. Probability of being within 8 meters is 0.99, right? So forth. So the GPS sensor will give you the likelihood data, the distribution. So this is easy to get from your sensor data sheet, or from the sensor's measurement quality. This is typically given to you, right? For example, for your IMU, you will know that your noise is Gaussian distributed around the mean. That is this value. Okay, very good. Denominator, who cares? Because we only want to compare the numerators for different values of SK. Does that make sense? The denominator always stays the same because the measurements are given to you, right? And all I need is, I want to basically figure out the numerator, which value of SK equals L1, L2, L3, which value of SK maximizes that denominator, that numerator probability. So I really do not care about the denominator, because even if I did not know the denominator, I don't care, because the numerator is the only thing I care about and the denominator stays the same. So denominator, I don't care. What is Sk? Now, if I tell you what is Sk, this depends on where I was last. So Sk is a function of, it's a function of Sk minus 1. You see that? If I say, what is the probability that Sk, what is the probability of Sk equals L5? How can I say it independently, right? My measurement says something that Sk, my measurement says that Sk is at L3. And now I'm asking, what is the probability of Sk equals L5? And from my motion model, if my motion model says, you know, Sk was at L4 in the last time step, then I know what is the probability of Sk equals L5, because I know the transition probability matrices, right? So Sk, this probability Sk is going to come from motion models. This is going to come from measurements, and I'm going to combine the two. Okay. So I said all this because I wanted you to get an intuitive feel of what this entity embeds inside it. Okay. Now let's go and get into math. Okay. Remember, what do we want? We are again going to start from here. Let's start from here again. We did this just for intuition, and now we are going to do this mathematically. We want Sk, probability of Sk given M1 to N. Actually, this is the offline version. You see, right? This is the offline version. Very good. So let's start with the basic result. And the basic result is, we are not going to do this. Instead, we are going to start with this. What is that? Who can tell me what this is in English language? P S1 through N given M1 through N.
Sort of like your trajectory over time.
Perfect.
Probability.
Exactly.
Is given the measure.
Exactly. This is trajectory given all measurements. Right? So instead of finding Sk, which is my location at K, I'm asking a broader question. What is the probability of every trajectory given all these measurements? Right? Imagine you are at the entrance of a shopping mall and imagine all the trajectories that you can walk. Right? I'm asking, what is the probability of each trajectory given all these measurements that your phone has picked up at the end of the trajectory, at the end of the walk? Right? That's the probability we want. And if we can pick the maximum of all those trajectories, that maximum, I will say, this is the path that the user walked. Very good. Okay, let's start. Again, I know the time. Let's just do for 5 more minutes and we'll finish. Good. So PS1 to N given M1 to N, if we write it as Bayes rule, we will write this as S1 to N, comma, M1 to N. PA given B equals PAB divided by PB. And this is proportional to, because the denominator doesn't matter. Doesn't matter for 2 reasons. One, I actually already have the measurements. Right? It's no longer a probability. I have the measurements. And 2, even if I did not have the measurements, I'm going to compare only the numerator because the denominator is going to stay the same for all values of S1 to N. For all different possible trajectories, the denominator is going to stay the same. So I only care about the numerator. Very good. So now let's look at the numerator. PS1 to N, M1 to N. How many dimensional space is this, guys? If I draw this distribution, this is the joint distribution of PS2N, M1 to N. How many dimensional space?
N
N
squared.
2n.
2N.
Two
Very
N.
good.
Yeah.
2N. Right? There are N variables here, there are N variables here. Okay. So this is in 2N. Very good. So then I can apply chain rule. What did chain rule say? Remember, anyone remembers chain rule? P ABC, what is chain rule? Probability of probability of ABC equals what?
Probability of A given B, probability of B given C, and
Adil, one tiny mistake. You're almost
Probably
there.
A given BC, and then probability.
Given B. My laptop is not connected. Yeah, now it's connected. Okay, so that's chain rule. By using this chain rule, let me make this smaller, otherwise it'll be confusing. Now using this chain rule, I'll write the right hand side. I'll write it as Mn given M1 to N minus 1, comma S1 to N. You're happy with that? There's nothing to be happy about. If I write that, what can I write next? Now I write M N minus 1 given M1 to N minus 2, comma S1 to N. And I can keep doing that until P M1 given, what do you think is going to go after given?
it's still S1 to N.
Perfect, S1 to N. Now I write P Sn given S1 to N minus 1. And I keep going until I do PS2 given S1 PS1. I've just done chain rule, but I've done chain rule over 2n variables. Very good. Now I'm going to make an important observation. And the observation is the following. Focus on this one. This is saying the probability of getting this measurement given all the previous measurements and all the locations or the trajectory that I have been at. All the possible trajectories. Okay. Now, this is where we make a Markovian assumption, meaning when I make a measurement at time n, I'm assuming that the measurement only depends on the state of the object at time n, which is Sn, and none of the previous states. Mathematically, what I'm saying is this term, I'm going to write that as Mn given Sn, and I'm going to throw away M1 to n minus 1 and S1 to n minus 1. Why? Okay, first of all, I hope you see that there is no harm in throwing away M1 to n minus 1, right? I made a GPS measurement now. How does it matter what GPS measurement I made in the past? Right? My current GPS measurement is only dependent on the user's location, not on my previous GPS measurements. Does that make sense? Right? It is not no relationship at all. If I know the current user's location, that is all I need to know for my GPS measurements. In fact, one way to think about this is as, suppose you are GPS. You are a GPS chip. Okay? Imagine you are a GPS chip sitting inside the phone. And I say, hey, GPS chip, what is my location now? What information do you need? You're not going to ask me, hey, what was my previous GPS measurement? If I can give you my current location, that's all you need to say what your GPS answer is, what your latitude, longitude is. Right? So you can easily remove all the previous measurements. Now, what about S1 to n minus 1? This is where we are saying the GPS measurement is only a function of what your current location is. The previous location does not matter. Right? I mean, imagine, right? You're doing triangulation from the satellites to your mobile phone. What really matters is what are the propagation delays from the satellite to your mobile phone right now, wherever you're located right now. Where you came from to this current location, that doesn't matter anymore. Right? However, if this was acceleration or if this was velocity, then maybe if this was velocity, then you need to know the previous location. Because the velocity measurement depends on the difference between the two locations. If it was acceleration, what would you need?
Would you need all of them?
Not necessarily. Why? I
Because
can calculate the acceleration from what is the minimal information that I need. Last how many locations?
we just need
Acceleration.
like a running counter of the last one or from the last time, and then you just add your contribution from the current time to the last one. I'm not sure.
Wait, so a user is walking like that. This is Sn. This is Sn minus 1. You know the location, you know the distance between this. Can you tell me what is the user's acceleration from Sn and Sn minus 1? You can tell what the user's velocity is, but can you tell the acceleration?
No,
You cannot.
no.
But now you know this as well, let's say Sn minus 2. Now can you tell the acceleration? You can compute one velocity here. You can compute one velocity here. And you can see what is the change of velocity. That tells you the acceleration.
I see.
Okay. So here we are assuming, actually, if you want to do IMU, you need to do Sn. If it was IMU, we need to do Sn minus 2 colon n for acceleration. But you know, we are not, I mean, that makes things a little bit complicated. So we are not going to do acceleration. In fact, in your MP, you're not going to do acceleration. You're going to do a self-driving car, and his GPS measurements will be given. So if it is a GPS measurement, then SN is fine. Guys, is that confusing? Or is that clear? If it's confusing, please go back and think about it. Very good. So I made that Markovian assumption. Mn does not care about M1 to n minus 1, does not care about S1 to n minus 1, only cares about Sn. Because if you are that GPS chip, you only want to know where you are currently, because based on that, your measurements will come out. What is the next one then? The next term? This term will become what? With that Markovian assumption? P of m n minus 1 given what? Markovian. So at the n minus 1th time, that measurement, that GPS measurement, will only depend on
Sn minus 1.
Sn minus 1. Right? I keep going. M1 will only depend on S1. Then Sn will depend on S1 to n minus 1. S2, sorry. Guys, another Markovian assumption. Sorry, I wrote this. Doesn't matter. It doesn't matter. Saying what I'm going to do next only depends on my previous state. Okay, very good. Last point. So now if you look at this, look what I can write this as. I can write this as P of M1, sorry, M1 given S1 times P of S1. Basically, I'm taking this and this. That I've taken out. And now look at the rest. The rest is product of equals 2 to n P of Mi given Si times P of Si given Si minus 1. This is an important result to keep with you. Can someone make any observations? This is the last minute of our class today. Where do you get this? What is this? PSI given SI minus 1. Where will we go to find this information?
The table that we made earlier.
Exactly. This is your transition probability matrix, basically your motion model, right? What is this? This is your sensor error, right? So look, I have basically now formulated I still have not solved the problem, but I figured out a way to express what I needed, the trajectory given the measurements as a function of the sensor measurements error and the motion model. Okay. And this beautifully kind of decouples. So next class, we're going to start off by saying, now let's do P of Sk given M1 to N. And we are going to see how it nicely becomes an efficiently doable algorithm. Okay. One can solve this problem by brute force, meaning you can look at all possible Si minus 1, all possible trajectories, multiply it with these values, and you can figure out the answer. That will be like exponentially hard. That's a brute force method. But we will see how to do this efficiently. Okay. I definitely want you to go back and look at today's class, today's lecture, and make sure you're in sync. We haven't shown you how to solve this problem yet. We've just done intermediate steps, but make sure you understand what is going on in every intermediate steps. And then next class, things will just fall in place nicely. Okay, so here is what we have coming up next class. Okay, class ends over here, but I'll of course hang back and take any questions. Otherwise, please feel free to leave.
Professor, you said on the left side of this equal, it's like basically trajectory, right? Like resultant predicted trajectory. In the red. I can't hear you.
Guys, can you hear me now?
Yep. Yep, he can hear you.
Oh, I cannot hear you. Anyway, class is over. So please hang back and let me know if you have questions.
Can you hear me, Professor?
Yes, now I can hear you.
Okay, cool. I can hear you too. The left side of this equal in the red is basically just like resultant predicted trajectory, right? In the red. I can't hear you again.
Can you hear me now?
Yeah, I can.
Good. Okay. You're saying this one. Wait. Oh, okay. You're saying this one?
Yep.
Yeah. That
Okay.
says what is the joint distribution of, or what is the joint probability of the trajectory and the measurements.
Okay.
What does that mean in English language?
I suppose the probability that you measure a certain location and that you're actually at that location.
Correct. Exactly. Right. What is the, now this S1 to N you can think of as trajectory 1, trajectory 2, trajectory 3, so on till trajectory 1 million, right? Right? There could be millions, 1 million trajectory, right? So you're asking, what is the probability that trajectory 1 happened and these measurements happened for that trajectory? What is the probability that trajectory 2 happened and these measurements happened for this trajectory. So imagine one trajectory, let's say trajectory 3 is you are static. Make sense? That's one possible trajectory, right? You are static.
Yeah.
Now say measurements are saying, wow, your GPS is moving a lot, or your IMU is giving you a lot of motion. Then the probability of trajectory 2 equals static, comma,
Likely.
measurements 1 to n equals lots of measurements, lots of motion. This probability must be very low, right?
Yeah. Mm-hmm.
So you're essentially trying to ask which trajectories and measurements agree.
I see.
And
And
if they agree,
source are
the
likely.
probability of that agreement would give you a higher value.
Okay. Okay.
Right. Maybe I should just write that. Which trajectory and measurements are in agreement?
And then can I ask you one more quick question?
Sure.
Would you mind scrolling up to the previous page a little bit?
1 second, please. 1 second. Let me just move this a little bit. Scrolling up where?
To the previous page, the bottom of it. I think it was right. Yeah, so right here. Sorry, I'm just trying to remember what
Sure. Sure.
The intuition behind so at that line where it says turn this posterior to likelihood, that
Right.
the intuition behind probability of M1 to N given SK, the intuition behind that is sort of like the reason we can go M1 to N given SK, like we can go beyond K to N. The intuition behind that is sort of like if I'm next to a tree, it's very unlikely that 30 seconds later I'm going to be hundreds of miles away from the tree, right? Like we can sort of predict that like you're likely to keep measuring my
Exactly.
somewhere in the vicinity of this tree even after like a few seconds after. Like I can't get
Exactly.
that.
Because
Okay.
that's what my motion model says.
Right.
Right?
Okay.
If the
Right, you
motion
can't go
model
that
says
far.
that you cannot travel at lightning speed, then if you're at near the tree, the next time instant you expect to be somewhat near the tree as well.
Right. Okay. That makes sense. So you can kind of look into the future a little bit.
You can. I mean, we're going to get
Future,
into
but
that.
predict.
Yeah. We're going to get into that you can look into the future a little bit, because your future measurements have to agree with whatever past locations you are at.
Nice. Okay. Yeah, that makes sense.
Yeah. In fact, that is what we are going to see next class, where we are going to look back and look into the past and look into the future, and both are going to give us information. So we are very much going to see that in the first 10-15 minutes of next class.
Interesting. Okay, thank you.
Great.
Professor, I had a question on just like that
Please.
last equation that we finished with.
Which one? This. Okay. Yes,
The
this
one in the
yes.
red, yeah. Are the first two then?
Yes.
Are the first two
Anthony,
terms?
sorry, Anthony, it was breaking. Can you try again,
Yeah.
please?
For the first two terms, is that saying like the intuition behind those first two terms? Are they basically saying the sensor error of the first measurement compared to like your initial location, and then what's the probability of you being in that first location?
Exactly.
Okay.
Right. So this is the initial condition.
Mm-hmm.
Right. In fact, we are going to talk about that too. This is saying what is the probability of your starting point, right? So if you think of S1 as L1, L2, L3, all the way till LR, if you don't have any information about the initial point, right, then you are going to say probability. Anthony, can you hear me?
Yeah, I can hear you.
Right. So then you make it equal probability, right? So PS1 is going to be 1 by R. But if you have some other information that says, no, this is a shopping mall, people are likely to start at the entrance. So you can, if you have some information about the initial location, you can put it here. This says, if your initial location is something, L1, L2, L3, whatever, what is your measurement likely to be for that location? So this is really your initial condition that you initiate your system with, and then you let it play it out. Then you play it out. If you do not have any initial information, even then the hidden Markov model will work. It will just look for all trajectories that do not start from a particular location. Instead, it starts from every location.
Got it. Okay.
Right.
Yeah.
So another way of looking at it is, if you have initial conditions as, oh, the user started from L1, wait, let it scroll. Let's say you know the user started from L1, right? Then all the trajectories are like, right? These are all trajectories, all possible trajectories. They all start from L1. But if you had no information about the initial one, you would have that same thing starting from everywhere.
Got
right?
it.
Because you do not know anything about the initial location, right? And then your measurements are going to say, look, if you started at this location, and if your second measurement says you're at this location, they don't agree. So then you say, hey, look, it's very unlikely that you're starting at LK. You're likely starting somewhere over here, because your second measurement says you're here. Anything else?
No, I think I'm good at my end. Thank you.
Perfect. Thank you.
Thank you.
Thanks. If there are no other questions, then let me end the class here.
Professor, I guess I just had to. I can talk to you about the research real quick.
Right.
So yep.
Maybe let me stop the recording and then we can talk. Okay.
Yeah.
Great.